Objective 3.2, Properties of Rational Exponents. In this lesson, we want to be able to use the properties of rational exponents to evaluate and simplify expressions. Now, I will warn you up front, this is going to be a bit of a long lesson, and there's not going to be any guided practice problems like there are usually in our lessons, because what I mostly want to do is just show you lots of different kinds of problems where you can use our properties in order to simplify or evaluate. So we're going to start here with a little bit of vocabulary so that we understand what it is we're aiming for. For a radical to be in simplest form, you must apply the properties of radicals, remove any perfect nth powers other than 1, and rationalize any denominators. Two radical expressions are like radicals if they have the same index and the same radicand. Okay, so our key here is to understand that when we're talking about radicals, that the simplest form is going to be if we've applied all the properties that are possible, we have removed any perfect nth powers, and we have rationalized any denominators. Okay, that's what we're trying to shoot for when we're dealing with radicals. Let's see, there we go. Okay, so we're starting out here actually with something that should look very familiar to you. These are the properties of rational exponents. And what you should notice here is that the properties are the same ones listed before when we've dealt with exponents. They're the same exponent properties. The difference now is that m and n, which represent our exponents, can be any rational numbers. Before, our exponents could only be integers. But now we're saying that these same properties work even if our m and our n are rational numbers. Okay? And so just for some examples here, we can see that if I have 3 to the 1/2 power times 3 to the 3/2 power, that the property allows me to add my exponents, which would become 3 squared, and that would be evaluated to be 9. Excuse me. The second property tells me that if I have 4 to the 3/2 power and then I square that, I'm allowed to take the 3/2 times the 2, which would be 3. So then 4 to the 3rd power would just give me 64. In number 3, excuse me, I can see where I have a product of 9 times 4. The whole thing is being taken to the 1/2 power. The property allows me to take the 1/2 power of each factor. And so 9 to the 1/2 is the same as square root of 9, so that's 3. And 4 to the 1/2 is the same as the square root of 4, so that's 2. And 3 times 2 would simply give me 6. In the next example, we have 25 to the negative 1/2 power. So as we mentioned before, a negative exponent simply means that we want the reciprocal. So we want 1 over 25 to the positive 1/2. Since 1/2 means square root, taking the square root of 25 would give us 5, and our overall answer would be 1/5. In number 5, we can have 6 to the 5/2 power over 6 to the 1/2 power. The division allows us to subtract our exponents, and so if we take 5/2 minus 1/2, that's going to be 4/2, or 2, and 6 squared would leave us with 36. And in number 6, if we're taking the fraction 8/27, all of that to the 1/3 power, our property says we can take the numerator and the denominator each to the 1/3 power. 1/3 means cube root, So cube root of 8 would be 2 for the numerator, and the cube root of 27 would be 3 for the denominator. So we're starting to get an idea here of how the properties can be applied even in situations where our exponents are rational numbers. Now, these exponent properties also kind of spill over into what we would call the products of radicals. And we have two major properties of radicals. The first one is called the product property, and it looks like this. Now, if you think about what that would look like if we wrote it as exponents, we would be saying that A times B, that product to the 1 over n power, is the same as A to the 1 over n times B to the 1 over n, which is exactly what one of our properties allows us to do. We can take the exponent of each factor separately. So the product property in our radicals is really just the radical form of our power of a product property from the exponents. Okay? This property is quite useful in both directions. For example, I can start out with something like the square root of 45. I can consider 45 to be my product, and I can say, well, the factors of 45 would be 9 and 5. So I can take the square root of those separately, and because 9 is a perfect square, I can take the square root of 9 and get 3, and then I have 3 square root of 5. We've seen that in our previous lessons, and this is why we're allowed to do it. But we can also use the property as a way of putting things sort of back together again. For example, in this problem, I have the cubed root of 4 times the cubed root of 2. Well, neither 4 nor 2 is a perfect cube, so I can't take the cube root of either one, nor do either one of them have a perfect cube factor. But if I put them together by multiplying the 4 and the 2 together, then I get the cube root of 8. And 8 is a perfect cube, so I can take the cube root of it, and I can get a final answer of 2. So the property works well in either direction, either starting with a product and splitting it up into the factors so that we can simplify, for example, or taking two radicals with the same indices. That is key, it does have to be the same indices, but taking two different radicals and multiplying them together to actually combine them and hopefully get something that we can actually take the root of in order to simplify it. Similarly with the quotient property, again, if you think about what this would be as exponents, we would be saying that I could take A over B all to the 1 over n power. And that would be the same as taking A to the 1 over n over B to the 1 over n. Okay, so again, same property, but written in radical form. And so the radical property actually says if I'm taking the root of a quotient, A over B, then I can take the root of the numerator and the root of the denominator separately. And again, this property can work in either direction. I could start off with the root of something like 9/16, and then I can take the square root of the 9 and the 16 separately to end up with an answer of 3/4. Or I could have something like the cubed root of 32 over the cubed root of 4. If I combine those and make it the cubed root of a single fraction, like 32/4, then 32/4 can be simplified to just 8, and again, cubed root of 8 would give me 2. So again, this property can be used in either direction, either taking the root of a property and the root of a radical and splitting it up into two radicals, or taking the quotient of two radicals and putting it back together so that you're taking the root of a single quotient and simplifying from there. All right, so those are kind of the basics that we have to work with today. So let's just start going through lots of different examples of how that might look in the problems you see on quizzes, tests, practice, whatever you might face. So in the first example, we have 6 to the 1/2 times 6 to the 1/3. The property says that if I have the same base, then I can add exponents when I'm multiplying the powers. But in order to add 1/2 and 1/3, I would have to get common denominators. So I change 1/2 to 3/6, I change 1/3 to 2/6, and then I can add my exponents and get 6 to the 5/6 power. In my second example, I have 27 to the 1/3 power times 6 to the 1/4 power, all being squared. Now I can do this in a couple of ways since I'm dealing with all numbers. I could take the cubed root of 27 and I could try to take the fourth root of 6 first and then take those things and square it. Or I could actually take 27 to the 1/3 power and square it by multiplying my exponents. And the same with 6 to the 1/4 power, I could square that by multiplying my exponents. I decided to do it that way first, to actually take each one and square it. And then from there, I used our property from last lesson that says if I have 27 to the 2/3 power, that means taking the cubed root of 27, since the 3 is on the bottom, and then squaring that answer. So the cubed root of 27 is 3. When I square it, I get 9. So that's the 9 that's out in front. And then with my 6, since the 2 over 4 gives me 1/2, I cannot actually take the square root of 6, nor does 6 have a perfect square factor in it that I could simplify, and so I'm going to have to leave that factor as 6 to the 1/2 power. So 9 times 6 to the 1/2 is about as simplified as you can get in this case. Now in the next example, we've got 4 to the 3rd power times 2 to the 3rd power, all being raised to the negative 1/3 power. Again, there are some different options on how you can go about this. I chose to take each factor and raise it to the negative 1/3 power first, which leaves me with 4 to the negative 1st power times 2 to the negative 1st power. Then I'm going to deal with the fact that those are negative exponents. If you remember from previous lessons, one of the other things about being simplified is that we cannot have negative exponents. So I'm going to change 4 to the negative 1st to 1/4, and 2 to the negative 1st, I'm going to change that to 1/2. And now I can multiply those two together and get an answer of 1/8. A couple more types of problems here with numbers. I have 6 over 6 to the 3/4 power. In this case, I don't see an exponent on the 6 in the numerator, and so I have to assume that that must be a 1. And so because I have a quotient, that means I can subtract my exponents, and 1 minus 3/4 will give me 6 to the 1/4. And again, this is a root that I can't actually take on 6, so I just leave it in that form. Now in the next example, I've got 18 to the 1/4 over 9 to the 1/4. All of that is being cubed. And so I can think of this, because my exponents were the same on the 18 and the 9, one way to think of this is to actually pull the 1/4 out, so to speak, so that the 1/4 is acting like a common exponent on the whole thing. And then I have the 18/9 here. And the reason that's helpful is because I can actually take 18 divided by 9. So when I do that, 18 divided by 9 will give me 2, and then the 1/4 to the third power will give me 3/4. So I end up with a simplified answer of 2 to the 3/4 power. Now, those examples were all written in exponent form. What if we decide to use radical form instead? So here I'm taking the cubed root of 25 times the cubed root of 5. Neither 25 nor 5 can be taken the cubed root of. But if I use my property, I can multiply the 25 and 5 together to get 125. And then I can take the cubed root of 125 and get 5, because that is a perfect cube. Similarly with our two radicals in the fraction down below, I have the cubed root of 135 over the cubed root of 5. Again, neither one can be taken cubed root of, but if I combine them and take 135 divided by 5, I end up with 27. So the cubed root of 27 is now 3. So what about simplifying a radical? All of our examples up to this point were simply about combining things and using the properties, but how do we make sure that we simplify correctly, especially when it's not just a square root? Well, we have to use sort of the same idea as we did with square root, and that is, with square roots, we had to have something as a factor that was a perfect square. And if that happened, then we could take things out. Okay? If I'm taking the fourth root, then I need a factor that is a perfect fourth power factor. So something being taken to the fourth power that can be a factor of the number inside the radical. Now you may be thinking, oh my gosh, how am I ever going to figure those out? But there's actually a quite simple way of doing that. If you remember from previous classes, when you were asked to find prime factorization, maybe you were asked to find it in a tree where you split it up and you went, well, I'm pretty sure 64 is 8 times 8, and then I could split up 8 into 2 times 4, and you keep going. That would be one way that you could do it. But I think it's a little bit easier to do another method, which is called inverted division. And in inverted division, we take our 64 and we're going to divide it, but we put an upside down division sign around it. That's where inverted comes from. And then the only rule is, there's two rules, I guess. We can only divide by prime numbers that come out evenly, and we have to keep dividing until we get to 1. Okay? So if I take 64, for example, I know I can divide by 2, and that leaves me with 32. I can divide that by 2 also, which leaves me with 16. Divide by 2 again, I get 8. Divide by 2, I get 4. Divide by 2, I get 2. And divide by 2 one more time until I finally get to my 1. Okay? Now, because I have a fourth root in my indice, in my index, the trick to this is to find a factor, like 2, that happens in a group of 4. So if I can group 4 2's together, then I know I have a perfect fourth power factor in 64. Okay? And that 2 then is what is going to come out of the radical. What's left here, let me change colors on that, or let's just highlight it. What's left here, that is what has to stay inside of the radical. So the 2 as a factor, because I can group it as 4, that 2 comes outside, and then I would be left with 4 on the inside. So how many you need in the group here is determined by what your index is here on the root. And they don't necessarily have to be in order. You just need to be able to group that many of the same prime factor together to be able to take that prime factor and put it out in front. And then whatever you can't take out, that gets left inside. Okay? So in a very mathematical way of doing this, you can see we're going to split up 64 into 2 to the 4th times 2 squared. Then using our property, we can split up and take the 4th root of 2 to the 4th and the 4th root of 2 squared, the 4th root of 2 to the 4th, the 4's cancel out, and we'll just have 2 4th root of 4 left as our answer. Okay? Now, the other rule in making sure that we have simplest form with our radicals is that we have to rationalize the denominator. So in a problem like this, where we're taking the 4th root of 7/8, we have to consider that this is really the 4th root of 7 over the 4th root of 8. And since we're not allowed to have roots in the denominator, we have to decide what to multiply by in order to get rid of that radical that's in the denominator. Now when we did square root of 5, if it's the square root of 3, then I multiply by another square root of 3. And with square roots, that works because you are taking a number, multiplying it by itself, so you're creating a perfect square that you can then take the square root of and get rid of the radical. But when your roots are something else, you have to do this a little bit differently. You're not just going to take the 4th root of 8 and multiply by the 4th root of 8, because that's not necessarily going to give you a perfect power of 4 answer. So you have to think about this in terms of what can I multiply by, or what do I need to multiply by, so that I do end up with a perfect 4th power answer inside of the radical. Okay, and so I think it helps to start out by thinking about, again, what is the prime factorization of the number inside the radical in the denominator. So if I think about 8, 8 is really 2 times 2 times 2. That's the prime factorization, and we can write that as 2 cubed. So what that tells me is that I already have excuse me, 3 2's in the group. What I need in the group in order to be able to take it out of the radical and get rid of the radical altogether is 4 2's. So how many more 2's do I actually need in this case? I only need 1 more. So that now I have the 3 2's here times another 2 here, which will ultimately end up giving me a group of 4 2's, which I can then take the 4th root of. So my denominator now becomes the 4th root of 2 to the 4th, and my numerator becomes the 4th root of 14, because the 7 times the 2 is just going to give me 14. Now remember, radicals in the numerator are not a problem. So I don't have to worry about the fact that I still have this radical of fourth root of 14 in the numerator. What I do want to take care of is that fourth root of 2 to the fourth now. The fourth root and the fourth power cancel each other out, and so all I have left is just the 2 in my denominator. I have just rationalized my denominator for a fourth root number. So the fourth root of 14 over 2 is my final answer. Notice we did not go an extra step and try to say it was the fourth root of 7. I cannot take a number that is not inside a radical and try to divide it with a number that is inside of a radical. Okay, there's no property that allows me to do that. So that 2 got to go outside of the radical. It's in a different place. It has a different set of rules that it follows now than the 14 that is still inside of the radical. And so those two numbers cannot be combined. They cannot cancel each other out in any way. The only way you can cancel numbers is if they are both inside the radical so you can combine them, or both outside the radical so you can divide them off. So it's fourth root of 14 over 2 would be your final answer in this case. All right, now what do we do with something like this? We've got 5 times 4 to the 3/4 power minus 3 times 4 to the 3/4 power. And what you need to realize here to the 3/4. And if you think about actually factoring that out, then the 5 minus 3 would leave you with 2. So you can kind of think of these like exponential terms, kind of like having an x. If I asked you what 5x minus 3x was, you would tell me it was 2x. Okay, like terms, same variable, we can subtract them. But what's really happening is that we're saying they both have a common factor of x. That leaves me with 5 minus 3, and that ends up giving us the 2x. So that's what's happening here. The fact that we have these common factors that are in the exponential form is kind of like working with an x. We can take the numbers out in front, we can do whatever operation with those numbers, and then still keep this common factor as part of our answer. Similarly, if I have a problem like the next one where I'm taking the cubed root of 81 minus the cubed root of 3, currently these are not like radicals. The definition said they had to have the same index, which these do, but they also have to have the same number inside the radical, which these do not. But if I take a look at the cubed root of 81, I should recognize that I can simplify this because there is a perfect cube factor in 81. 81 is 3 times 3 times 3 times 3, 3 to the 4th power. And you notice here I've just rewritten it as 3 cubed times 3 to emphasize the fact that the 3 cubed gives me enough 3's in that group that I can take them out because my index is a 3. So this term right here becomes 3 cubed root of 3. So I'm taking the cubed root of 3 cubed, and then this 3 has to stay inside. Okay, now I'm subtracting another cubed root of 3. So now I do have like terms because they both are dealing with cubed roots of 3. So if I have 3 of these, minus one of these, I end up with 2 cubed roots of 3. Because again, this is our common factor that's going to stay in our answer. All right, moving right along. So now, whoops, don't want to do that quite yet. So all of the examples you've seen so far have dealt with strictly numerical expressions. We've had numerical bases, we've had numerical exponents, we've been able to actually work some things out, combine them, simplify them, and get kind of a final answer. But now we're going to take a look at some expressions involving variables. And so when we have variables, we have to understand there's a certain part of this problem we don't really know what it's equal to. So we still want to simplify as much as we can, as best we can, but we're going to probably still have variables in our answer when we're all done. And one of the things that you always need to realize when you're dealing with variables is that we must assume that all of our variables are going to be positive. So unless you see some other direction that tells you differently, we will always be assuming that our variables represent positive numbers. Okay, because if they didn't, then we would have to be extra careful about taking even roots when odd numbers are around, and that just gets too confusing. Okay, so we're going to assume that our variables are always going to be positive unless you're told differently in the problem. All right, so when you're faced with something like the cubed root of 27z to the 9th, the idea is still the same. We're still trying to find perfect cube factors this time because we have 3 for our index, and we can break it down using properties of radicals. So I can start by realizing that 27 is just 3 cubed, so that gives me one group of 3 factors, and that factor is a 3. So I get 3 3s out of 27. Now with the z's, I actually have 9 z's. Z to the 9th means I'm multiplying z 9 times. So if I start grouping those into groups of 3, you'll notice that I have 3 different groups of 3z. So I have one here. Oops, sorry. Let me go back here quick. Okay. So you can see here I have one group of 3z's, 2 groups of 3z's, 3 groups of 3z's, and that makes up my 9z's total. So now if I use the property and break them all up and take the cube root of each factor separately, the cubed root of 3 cubed will give me 3. The cubed root of z cubed will give me z, excuse me. And that happens 3 times. So now z times z times z ends up giving me that z cubed, and the 3 that I had here gives me that 3 out there. Now the shortcut to this is that when I have a variable taken to a power, and I have an index out here that basically says how many need to be in each group for me to be able to take it out of the radical, I simply take my exponent, divide it by my index, and because that goes 3 evenly, that 3 tells me I end up with z cubed when I take it out of the radical. Now if this had been z to the 10th, and I divide it by 3, I would get 3, which gives me 9, but then I'd have a remainder of 1. And so that means I would have to have z cubed on the outside. This still tells me what goes on the outside, but my remainder tells me what has to stay on the inside. So I would still have 1z left on the inside of the radical if I have a remainder when I divide. So that's kind of a shortcut on figuring out what your factor will be when you take it out of the radical and what, if anything, will be left inside the radical in terms of the exponents on those factors. Okay, how about this one? We're looking at 16g to the 4th h squared all to the 1/2 power. So I can use the property that says each factor gets taken to the 1/2 power, and then realize that 1/2 power is the same as square root. So 16 to the 1/2 power means square root of 16, I get 4. In the g and the h factors, my exponent is being taken to another exponent, so I'm going to multiply them. 4 times 1/2 is 2, so I get g squared. And the 2 times 1/2 is 1, so I just get an h. So when I put all the pieces back together again, I end up with 4g squared h as my answer. Okay, how about this one? When we have a problem that has several different pieces to it, we need to try to think about which pieces go together. And usually numbers go with numbers, and exponents with the same base go with other exponents of the same base. So in this case, I should be able to group the 18 with the 6 here, because numbers go with numbers. And I can put this r on top with the r to the 1/4 on the bottom. The s and the t are the only s and t factors in the problem, and so I shouldn't have to combine them with other things. I just need to deal with them as is. Okay? And so what we end up with then is taking 18 over 6, taking the r on top over the r to the 1/4 on the bottom, the s on top with no s on the bottom means that it's just going to be 1 in my denominator, and then the t to the 1/3 in my denominator with no other t on top, we're going to write that as 1 over t to the -3. And then we're just going to evaluate each piece separately. So 18 over 6 is 3. I take r to the 1st power over r to the 1/4. That means taking 1 minus 1/4 and getting r to the 3/4 power. The s is in the numerator. It already has a positive exponent, and there's no other s to combine it with, so I'm really not going to do anything with that. It's just going to stay s to the 2/3 power. But my t, which is currently in the denominator, has a -3 exponent on it, and I need to make that negative exponent positive. So I'm going to do that by taking the reciprocal, moving the t up to the numerator, and making it t to the +3 power. And then I just combine them all back together to get a final answer of 3 r to the 3/4, s to the 2/3, t cubed. Okay. What if I want the 4th root of 12d to the 4th, e to the 9th, f to the 14th? Again, probably the easiest way to do this is to divide it up into the separate pieces. So I'm going to take a look at the 4th root of 12, the 4th root of d to the 4th, the 4th root of e to the 9th, and the 4th root of f to the 14th. Now, the way that I usually do this is once I chunk them up like this, I just make myself a radical, and then I start evaluating each piece, and I put the things that can go outside on the outside, out in front, and the things that go inside stay on the inside. So for example here, the fourth root of 12, it's not a perfect fourth power. It doesn't have a perfect fourth power factor in it because 12 is just 2, 2, and 3, right? So no groups of 4 there at all. And so that 12, there's nothing about it that can come out of the radical. So it's going to stay. Then I get to my fourth power of d to the fourth. Well, d to the fourth already means I have 4 d's being multiplied. So that means, since it's the fourth root, the d can come out in front. Next I have e to the ninth and the fourth root of that. So again, if we go with my little trick I showed you a minute ago, if I take 9 divided by 4, that's going to go twice and leave me a remainder of 1. So that means e squared gets to come out because I have 2 groups of e that have 4 e's in it, but then there's still 1 e left that has to stay inside. So that's what we're seeing here. And then the same idea here with my f to the 14th. If I take 14 and divide it by 4, that's going to go 3 times to give me 12 with a remainder of 2. So I have f cubed that gets to come out, and then 2 f's, f squared, that has to stay inside. And so my final answer ends up being d e squared f cubed out here in front of the radical, and then the fourth root of 12e f squared is the other piece of it. That's the part that has to stay inside of the radical. All right, what if we need to take the fifth root of g squared over h to the 7th? Well, again, our goal is to try to get a denominator that has enough factors that I can take the fifth root of it. Okay, so if I take the fifth root of the top and bottom separately, then you can see here I end up with the fifth root of h to the 7th power. So how many more h's do I need so that I can divide by 5 evenly? And so I choose 3 h's, which ends up giving me h to the 10th. And when I take the fifth root of h to the 10th, that's going to give me h squared, and the radical is now gone. Now, because I multiplied the bottom by the fifth root of h cubed, I also have to multiply the top by the fifth root of h cubed. So that should be a 3 there, not a 2. Okay, which means that when I multiply my g squared times my h cubed, I should be getting the fifth root of g squared h cubed in the numerator. And I got it right here. I just kind of messed it up here. So this is our final answer, the fifth root of g squared h cubed all over h squared. All right, last bit here. So if you have a product in your term or a portion of your term that matches up from term to term, then you have like terms. So what I mean by that is, in this first example, we have 8 square root of x minus 3 square root of x. That square root of x is a match in both of these. And so again, we can think of it like a common factor, and we can actually take the h the 8 minus the 3, and we can say that this is going to be 5 square root of x. Now in the second example, we actually have this whole gh to the 1/4 that is common, and so that whole thing is going to be the common factor that makes it a like term. And so all we need to do is take the 3 minus the 6 and get -3, and then gh to the 1/4 stays that common piece. And similarly, down here in our last case, the 4th root of 6x. Now this one has the 5th and this one doesn't. So at the moment, they are not like terms. But if I simplify x to the 5th, because I have a 4 for my index, that means I can take an x out and leave one x on the inside. So this becomes 2x 4th root of 6x, and then plus an x 4th root of 6x. And what ends up being the like term in both of these is the whole x 4th root 6x part. So I end up with 2 here, 1 more here, ends up giving me 3x 4th root 6x as an answer. Kinds of common factors in your terms, use them to make them like terms and combine them together. When you don't, like in the last one, try to see if you can make it match so that you can make them be like terms and then can combine them together. So there's our 5 square root of x, our -3gh to the 4th, and our 3x. That was a lot, and I apologize for that, but I hope that no matter what kind of problem you now see in your homework, you'll have something that you can go back to, you can look at, you can see this is how we did it on this example problem, and hopefully transfer that to what you need to do on your problem. There's a lot of different types of problems that you can simplify using the properties, and you need to be able to simplify using the properties. And so I went through a bunch of them for you today. If that was a lot, take a break for now, come back to them a little bit later, maybe go back to just the ones that puzzled you a little bit, watch that part again, and make sure you really understand what the steps are and what the processes are that allow you to do this kind of simplifying, because as we continue with this chapter, one of the big things we're going to need to be able to do is to simplify things to make them easier to work with. Okay? Once you think you've got your head around all of the different examples and all the different possibilities, then you're ready to work on the practice problems in Objective 3.2. If you do have any questions and you can't quite figure it out from the video, ask questions, find some other resources, look in your textbook, shoot me an email, whatever you need to do, but make sure you understand how to do these kinds of problems, and don't forget to check your answers once you've completed your practice looking at the answers on Canvas. Okay? Promise next lesson won't be quite so long. Thanks for hanging in there with me. We'll see you next time.